In my previous video that was introducing you to systems of differential equations, we tried this little toy example here. X prime equals half x minus y prime equals blah blah blah. And we went ahead and we tried to find a solution of the form e to the lambda t u. After a bunch of work and stuff and dividing by e to the lambda t, we ended up coming across this equation here, au equals lambda u. Now, if you've seen my previous two videos on systems of differential equations, and then more importantly, my video crash course on linear algebra, you've seen this equation before, and you know how to solve it. You'll recognize that this is the eigen problem. So the important point to make then is that if you have a system of differential equations like this that's linear, that you can represent with a matrix A, then solving it is as simple as solving the eigen problem for your matrix. So let's do it now with a new example. And what we're going to do is we're going to not only solve it, but also draw a picture of our solutions, and it should be pretty interesting what we get. So let's get into it then. So we can rewrite this system in the form x prime equals ax, where A is this matrix, and of course x, as always, is referring to the vector x, which has components x of t and y of t. So it's just a compact notation. So this is our matrix, and then we go ahead and we try to solve the eigen problem. Au equals lambda u, and whenever we solve it, the result, lambda and u, go in here and tell us the solutions to our differential equations. So first, we have to find the eigenvalues. Those are the values of lambda that make this possible. And instead of doing it by hand, since the numbers are kind of hard, I've decided to show you how to do this with Mathematica. So you can enter a matrix, and then you can also define the identity matrix for convenience. And then solving this equation, you just type it in just as I wrote it. Mathematica does have a determinant function, so that's capital DET. Determinant of a minus lambda I equals 0. Unfortunately, you can't write I here because capital I is actually used for something else. Actually, it's used for the imaginary number. So we have to use ID for identity. Anyway, when we solve a minus lambda identity, determinant equals 0 for lambda, it tells us that lambda is 3/100ths or 1/20th. Those are the values of lambda that make this happen. 3/100ths and 1/20th. So the eigenvectors corresponding to these eigenvalues, well, that means that we have to solve the equation a minus lambda I u equals 0, which I somewhat clumsily did not write down. So let me write it down now. A minus lambda I times the vector u, which I'll put a little hat on him, is equal to 0, by which I mean the 0 vector. And then you'll recall that the only reason this was possible is because a minus lambda I is a singular matrix for these values of lambda. That was the whole point in finding these values of lambda. And because it's a singular matrix, it has a null space, and that's what we're trying to find. So I just said, please find the null space of this matrix. And because I asked very nicely, Mathematica did it for me and told me that a vector in the null space is 1/2, 1. And when I asked again, very politely, for the null space of corresponding to the other eigenvalue. Mathematica kindly told me that 5/2, 1 is a vector in this null space. But you'll recall that what am I trying to say? These null spaces, they don't just consist of one vector now, do they? They consist of an entire line of vectors. Now, I thought it was kind of silly that Mathematica gave me 1/2, 1 as my vector, because the vector 1, 2 is also on that line, and similarly 5, 2 is also on that line. So I figured if I can have vectors with integer coordinates, I might as well use vectors with integer coordinates. So I multiplied these vectors by scalars, because it really doesn't matter which eigenvector we find as long as we find an eigenvector. So these are both perfectly valid eigenvectors, 1, 2, and 5, 2. And so we conclude that our general solution is, well, it's just going to consist of these e to the lambda t u's. Each one of them is a solution, and any linear combination of them will be a solution, it turns out. So this first vector is e to the 3/100ths t times the vector 1, 2, which gives us this. And then the second solution is e to the 1/20th t times the vector 5, 2, which is all of this. So this is my general solution to the problem. Now, I promised I would use the PPlane program in my presentation. Here it is. If you've downloaded it already, good. If you haven't, definitely do it, because it's awesome, and it will really help you to check your solutions and stuff. So this is the stuff I typed. All you do is, for PPlane, is you type in the original differential equation here. So just x prime equals what x prime equals, y prime equals what y prime equals, and you choose your window, and you don't have to worry about these parameter expressions, but they can be helpful in other contexts. But anyway, you get this. Well, actually, you get a blank screen, and then you click in various places. All these little dots are places where I clicked my mouse, and every time you click somewhere, it solves the system of differential equations with that point as the initial value. So what you get is pretty sweet, if I do say so myself. This is a whole bunch of different solutions, and all these solutions could have been found just by choosing different values of C1 and C2, which is pretty sweet. So you can really make a lot more sense of these solutions if you plot the eigenspaces, the eigenvectors, and their corresponding spaces. The eigenvectors, you'll recall, were 5, 2, and 1, 2. So I drew the lines through those two vectors. Those are the eigenspaces for our matrix. And then it turns out that we have solutions that are parallel to these eigenspaces. So basically what happens is it really, first of all, this point here, it's called an unstable node. I'll talk more about that. I'll talk more about that later, I think, but you'll find there's a lot of different funny patterns you can get for these linear equations, and this pattern is called an unstable node. Unstable means that solutions are veering away from the equilibrium as opposed to heading toward the equilibrium. So if I had actually used a different vector field, maybe we could have had arrows pointing toward the origin, and solutions would actually be going toward the origin rather than away from the origin. And that would be called stable if the solutions are going toward the equilibrium. Stability is a really nice way of thinking about it, by the way, because like if you put a point right here, it's kind of balanced on the edge of a knife, because as soon as it moves even a tiny bit one way, then it'll start to veer off along the vector field. So quite literally is unstable, if ever there were such a thing. Let's talk about, so the behavior of these solutions comes from basically two things. One is the eigenvectors, which I plotted, 5, 2, and 1, 2. The other is the eigenvalues, 3 100ths and 1/20th. Now notice that 1/20th, or 0.05, is a bigger eigenvalue than 0.03, what we have over here. So the eigenvalue 0.05 corresponding to the eigenvector 5, 2, that's the green eigenvector, is dominant. This eigenvalue is dominant over this eigenvalue, meaning if you take a large value of t, like t equals 500, to be clear, both of these vectors are going to be immeasurably huge if you plug in t equals 500. But this vector will be immeasurably huger than this vector because the exponent is, because we have 500 times 0.05 instead of 500 times 0.03. So because of the larger exponent here, this solution is dominant for large values of t, meaning all the solutions end up roughly parallel to the green eigenvector over long periods of time. On the other hand, if you rewind the clock and let t go to negative infinity, then the solutions are going back toward the origin, and they actually come back roughly parallel to the purple eigenvector, because it turns out these numbers are much bigger than these numbers when you take large negative values of t. Why don't you think about that for a while in your cave, and eventually it might make some sense to you. But yes, so the size of the eigenvalues determines the dominance of one eigenvector over the other in the long term. All right, so perhaps you were dreading this, or perhaps you didn't even realize it was going to be an issue. But it is an issue. We can have complex valued eigenvalues. So what would you do if you came across such a thing? Well, thankfully, all the rules of linear algebra apply to complex matrices, complex spaces. So here's an example of such a problem where you get complex eigenvalues. If you want to find the general solution, then you rewrite the system in matrix vector form. You guess at the solution e to the lambda tu. You get the Eigen equation au equals lambda u, and now we know that we need to find eigenvalues satisfying determinant a minus lambda I equals 0. So we define A, we define identity, we solve the Eigen equation for the eigenvalue equation for lambda, and we get complex roots. Lambda equals 2 plus or minus the square root of 15 I, imaginary number I. So what do we do with these eigenvalues? Well, you need a little bit of complex eigenvalue theory. We're not going to prove anything in this course. This isn't a proving things course, so we will instead list some facts that you can take for granted, and you can take them to the bank because they have been proven by people who prove things for a living. Fact 1, if you have a matrix and you compute its eigenvalues, if you have imaginary eigenvalues, they will always come in complex conjugate pairs. So they will always come in these pairs a plus or minus bi. You can never have one without the other, at least if you started with a real matrix. I should really emphasize here that this is assuming the original matrix in your problem is real. So you can often get complex eigenvalues from a real matrix, as you saw in the problem on the previous slide. The point is, if the matrix is real, its complex eigenvalues will come in complex conjugate pairs. The next fact is that the eigenvectors will also come in complex conjugate pairs. And by the way, the eigenvectors will have complex numbers for their coordinates. That's a thing. Complex vectors, not just complex numbers. So yeah, but they will come in complex conjugate pairs. So if you find the eigenvector for one of these guys, the other eigenvector is just going to be the same vector, but where you take the complex conjugate of each component. The complex conjugate, by the way, in case you forgot or never learned this, if you have an imaginary number or a complex number a plus bi, then the complex conjugate just means take the same number but replace b with negative b. So a minus bi is the conjugate of a plus bi, and we often denote conjugation with a bar. So z bar is the conjugate. Anyway, and that's another thing, is we often denote complex numbers with the letter z. That's pretty popular notation, like if you have a complex variable. Anyway, all right, so these are two facts, but here's the bombshell. The bombshell is that if you just use one of the eigenvalues and you use the corresponding eigenvector, and then you use this solution e to the lambda tu through Euler's identity, then the real part will be a solution and the imaginary part will be a solution to your differential equation. And finally, the last fact, which is just kind of insurance for you, really, is that you won't find any different solutions by using the other eigenvalue. You would end up with essentially the same solutions. I say essentially because there's some shenanigans with the constants that might change, but the solutions will be essentially the same. You won't lose anything by just considering the first eigenvalue, lambda plus. Lambda minus will not give you anything new. I promise you that. So back to our problem, we found complex conjugate eigenvalues. Didn't I promise you they always come in complex conjugate pairs, even for higher dimensional problems? So even if you had a system of 5 equations and you wanted to solve the eigenproblem for a 5x5 matrix, you'll still have complex conjugate eigenvalues. So that's always the case. So, and the theory also told us that we only have to use one of them. So we can use 2 plus root 15i. If we use that eigenvalue, we can find the eigenvector. It's kind of annoying, really. This is doing complex number arithmetic is kind of cumbersome. So it's definitely a good idea to use Mathematica. So I found the null space, but when I typed this in, it gave me a kind of weird answer, so I used the expand function to simplify it. So this is what I ended up getting. So this is our null space. This is our eigenvector. 4th plus root 15 over 4i, comma 1 is our eigenvector. Here it is. And now, if we can get a complex solution, which I denoted x tilde, is found by taking e to the lambda 1t times our eigenvector. And then the theory from the previous slide said if you take the real part of this, you get a solution. And if you take the imaginary part, you get another solution. So our actual solutions are x1 and x2. This x tilde is just some complex nonsense that we use on the way there. So what is x tilde? What are x1 and x2? How do these computations look? Well, it's pretty hard, so let's go through this line by line. First of all, I defined Euler's identity, which is e to the zt equals e to the real part of zt times the cosine of the imaginary part t plus I times e to the real part of zt sine of the imaginary part of z times t, where z is a complex number. So we've seen this when we were studying higher order differential equations several presentations ago. This Euler identity. And so it's useful for us here as well. Then we agreed that our eigenvalue was 2 plus root 15I, and the corresponding eigenvector, after I took this and multiplied it by 4, because you can do that. There's an entire line of eigenvectors, so you don't have to use fractions. You can just use whole numbers. This is the eigenvector corresponding to lambda 1. And then I used x complex. That's my x tilde. X complex is e to the lambda 1t u1. That's our solution, but it's going to be complex valued. So what we have to do is take the real part of it. But before we do that, we have to first apply Euler's identity and expand so we can combine like terms. And then we take the real part. And finally, we have to refine our answer, assuming t is a real number. If you don't do that, Mathematica won't really know how to simplify this. I think I'll put some kind of an further explanation for that on my website, because I realize there's so much happening here. We're taking our original solution, we're applying an identity, expanding, taking the real part, and then this refining thing is probably pretty mysterious to you. If you're curious, you can always read the documentation for what refine does. Another thing you could do to understand this is try getting rid of the refine and getting rid of the t element of reals and seeing what happens when you just write this code. Because you can bet that that's the first thing I did, and you'll see it's not what you want. It doesn't simplify properly. So perhaps sitting down and tinkering with this code and reading some of the documentation can help you really understand what's happening here. You'll definitely want to be able to enter this code, because doing these computations by hand is just it's awful. It's not realistic. And the second solution is found by doing the same thing, but taking the imaginary part of our complex solution as opposed to the real part. So when you take the imaginary part, you get something else, and those are your solutions. So this is the first solution. This is the second solution. Hello, first solution. Hello, second solution. And any linear combination is a solution. This is the general solution. And no problem would be complete without a visualization. So if you stare at this, you see that, I'm just going to shut up. You can just admire for a second. Isn't that great? Okay. So by choosing different values of these constants C1 and C2, you get different spirals. So notice that the solutions are leaving the origin because the arrows are pointing away as opposed to pointing toward the origin, which means this is an unstable spiral equilibrium point. So that is the second type of equilibrium point that we've considered. Here is another system. 3x minus 6y, 3x minus 3y. Write it in vector matrix notation, guess, and solve the Eigen Equation. If you solve the determinant a minus lambda I equals 0, you get lambda equals plus or minus 3i. So we can focus on just the first eigenvalue, since this is a complex conjugate pair. You only have to use one of them and then take real and imaginary parts to get your solution. So the corresponding eigenvector after using Mathematica is 1 plus I, 1. The two solutions are found by taking real and imaginary parts. So you take the real part of e to the lambda 1t u1 and the imaginary part of e to the lambda 1t u1, and you get these. Using the same exact code from the previous slide for simplifying the real and imaginary parts and Euler's identity. Notice that we no longer have exponentials because this is pure imaginary, so you can recall that the real part is 0, which means that you don't have an exponential function in here. So take a moment to guess what you think might happen, and the spoiler is coming in 5, 4, 3, 2. Hold on a second. There's the spoiler. Okay, so the solutions are now slanted ellipses about the equilibrium. So this is actually really fun. So the idea is that the imaginary part, when you have imaginary eigenvalues, they give you sines and cosines, which give you these circular or elliptical type things. But then when you have a real part, that would ordinarily give you an exponential function in here that would cause the solutions to also spiral out and get bigger and bigger. Or if you had a negative real part here, then you'd have shrinking exponentials causing the solutions to spiral in and get closer and closer to the origin. But if you have exactly 0 for your real part, then you don't have any exponential part, so the solutions neither spiral out nor spiral in, they just orbit periodically in elliptical orbits. I did some analysis for you, and I found that these ellipses in this particular problem have an angle here. So if we draw the x-axis and we take the major, sorry about that line, if we take this angle, I figured out that it was 31.72 degrees. Actually, the amount of time I spent figuring that out, I probably could have gone to a store, bought a protractor, and used that faster. But nonetheless, I eventually was able to figure this out using some trig identities. And I also found, using those same trig identities, that the radii are 2.618 times longer along these directions as along these directions. And again, I also could have done that faster with a ruler. Yeah, so I actually found those computations were really hard. If you're in my class and you want some bonus points, you can go ahead and try to figure out how I got these numbers mathematically. It's really hard. It's surprisingly hard. You wouldn't think it was that hard Like, you'd think a couple trig identities would get you there, but it was a challenging problem. I was definitely at my blackboard for a little while doing that. On the other hand, the period is pretty easy to figure out. The period is just this number divided, or I'm sorry, 2 pi divided by this number. But of course 2 pi is tau. So tau over 3 is the period. So these solutions are traversed with period 2.094 units of time, whatever the units of time are for your model. And so this is a this is called a stable center. So you'll notice that each one of the problems I solve, I always state the equilibrium type at the end. So I believe we've seen 3 so far. We've seen a node, we saw an unstable node, we saw an unstable spiral, and now we've seen a stable center. Here's another differential equation. We go through the usual process of solving it. We guess e to the lambda tu is going to be our solution. That leads us to the Eigen equation. We solve the Eigen equation by solving determinant a minus lambda I equals 0, and you get eigenvalues 2 and -1. I've shown you the code for doing this, or I've shown you the equations for doing this by hand, and I've also shown you the code on previous slides, so I'm not going to copy the code here. You can rewind to one of the first problems. All the code is there for how you find these. So this time we have 2 real eigenvalues, 2 and -1, and the eigenvectors are found to be 1, -1, and 2, 1. Which are found by computing the null spaces of a minus lambda I for those 2 values of lambda. And therefore the solutions are this and this. And any linear combination is also a solution. And this is what the solutions look like. And if you plot the eigenvectors, or the eigenspaces, really, the lines going through the eigenvectors, you get this green one obviously is the first eigenvector, and the purple one is the second eigenvector. And you see that if you're on the purple line, the solutions are actually going toward the origin, but if you're on the green line, then solutions are actually going away from the origin. That has to do with the fact that you have the green eigenvector has an eigenvalue of 2, which points away from the origin, whereas the purple eigenvector has an eigenvalue of -1, which implies the solutions go toward the origin. So that's kind of a funny way of thinking about numbers, is positive real numbers point away from the origin, negative real numbers point toward the origin, and then for those spiral problems, imaginary numbers neither point toward nor away from the origin. So yeah, I guess that's a way of thinking about it. Honestly, I just thought of that now. Alright, this node is called a saddle node. And the reason I put unstable in parentheses is because all saddle nodes are unstable. A saddle node is characterized by a positive real eigenvalue and a negative real eigenvalue. And they correspond to solutions going toward the origin along one eigenvector and away from the origin along another eigenvector. And so what you have looks like the contour map for a saddle surface. If you took Calc 3, you know what I'm talking about, otherwise don't worry about it. But this looks like the contour map of a saddle, and that's why it's called a saddle node.